Today we have two talks. The first talk is given by Zhengtao Gan, who received his PhD degree in mechanics from the Chinese Academy of Science in 2017. He joined Northwestern University as postdoc after the graduation, then was promoted to research associate in 2019 and research assistant professor in 2020. He joined the University of Texas at El Paso as assistant professor in 2022. Dr. Gan's expertise involves additive and advanced manufacturing, multi-scale and multi-physics modeling, and scientific machine learning. Welcome, Dr. Gan, and you may want to share your screen and start your presentation.
Yeah, thank you very much, Songren, for your introduction, and thank you and George's invitation to this Machine Learning plus X seminar. Let me share my screen. Can you see my presentation?
Yes.
Can you see the apps here? Bar?
What's that?
Can you see a bar on the right side? Probably not, right?
No.
Okay, that will be fine. Okay. Okay, thank you very much and for this invitation. And I'm very delighted to be here and give a talk to talk about the paper we published recently. This work is entitled as Data-Driven Discovery of Dimensionless Numbers and Governing Laws from Scarce Measurements. And here is the author list. So this work was done at Northwestern University. So I'm Zhengtao Gan, and currently I joined University of Texas at El Paso last year as assistant professor. I'm also a joint assistant professor at Northwestern University. So basically in this presentation, I will just talk about the ideas and some examples of this paper. So I think this paper is aligned with our seminar that is Machine Learning plus X. So this paper is basically how to use machine learning to discover dimensionless numbers and laws from experimental or simulation data. It published in 2022 on Nature Communications. And the basic idea is that we proposed a method called dimensionless learning, which is equal to machine learning plus dimensional analysis. And we use that method, we can discover dominant and unique dimensionless numbers and governing laws from data, mostly experimental data. And we want to try to reduce the high dimensional parameter space to just a few dimensionless parameters, which are physically interpretable. So we want to interpret the results instead of just using a black box machine learning model to fit our experimental data. Okay. So mathematically or physically, all physical law can be expressed as dimensionless relationship with fewer dimensionless numbers and in a more compact form. It is well known in fluid mechanics. We can use Reynolds number to identify the pattern or flow pattern or flow state of the pipe flow. That distinguish the laminar and turbulence flow depends on the Reynolds number's value. And Reynolds number is a well-known dimensionless number discovered by Osborne Reynolds in 1883 paper. And basically it's a power law of four physical quantities: density, average velocity, and length and viscosity of the fluid. So we can combine these four dimensional quantities to become a dimensionless quantity. And another example would be in physics. So that's kind of a story. So the first explosion of an atomic bomb occurred in 1945. And at that time, a newspaper published some photos of this atomic bomb with this shape and with different time scale. And at that time, a very smart British physicist, J.I. Taylor, just based on those pictures or photos from the newspaper, and he can estimate the power released by the explosion. It's about 22 kilotons of TNT. And the military was shocked because that number, the power number, was definitely a secret. And the true value, based on the later report, is about 22 kilotons of TNT. So basically what J.I. Taylor did is just using dimensional analysis to figure out this simple scaling law, and just use the results from the newspaper to fit a parameter in the this scaling law, and he can like evaluate the power of the energy. Okay, so this kind of example shows the power or the strength of the scaling law or dimensionless expression or dimensionless parameters. And actually, nowadays, we have discovered more than 1,020 dimensionless numbers from very wide fields or areas, from physics or chemistry, even biology and engineering science. Okay, so it's a very powerful tool or powerful way to think about a problem. So there are a couple of advantages of describing a physical system using dimensionless numbers. The first is obvious. It reduces the number of parameters because we group some dimensional parameters together as a dimensionless parameter to describe the system. So basically, if we have a physical system, we can use several, we have an output parameter that we are interested in, and we assume it depends on several input physical quantities, and we have an unknown relationship between them, but we want to figure out a relationship between them. And we know the dimension of each of the parameter, and the dimension of them are just the power law of some fundamental dimensions such as length, time, mass, temperature, and so forth. And based on the dimensionless description, we can figure out another dimensionless expression involving fewer parameters. For example, initially we have 5, but after the dimensionless, typically we have 2 or 3 dimensionless parameters to describe the same problem or same physical system. So that's one advantage. Another thing, we rely on the dimensional analysis or dimensionless numbers to do cross-scale experiments. So for example, in this X-43 plane, hypersonic aircraft, so we can do small-scale experiments in a wind tunnel or in a lab, but we want to make sure these small-scale experiments have the have several similarities as its full-scale applications, including geometric similarity, kinematic similarity, or dynamic similarity. So basically, we need to have a set of dimensionless numbers, and to make sure those dimensionless numbers have the same values in our small-scale experiments as well as our full-scale applications. So even though our length scale or time scale are different, but we want to make sure those dimensionless numbers are the same, because those dimensionless numbers are scale invariant. Okay. And also, if we can figure out some dimensionless numbers for the problem, we can increase our physical interpretability, because typically a dimensionless number is a ratio of some forces or energies or mechanisms. For example, the Pechnik number is just a ratio of the convection rate of the physical quantity by flow over the gradient-driven diffusion rate. So based on the value of this dimensionless number, we can do order of magnitude analysis, even before we actually solve the equation, solve the problem. Okay, so these are a couple of advantages of using dimensionless numbers. So these slides will talk about the typical two ways to identify dimensionless numbers for a problem. The first is if we, for some classic system or classical physical systems, if we already know the governing equations of that system, we can simply just do a non-dimensionalization of that governing equations to get some dimensionless numbers. Those numbers are just the coefficient in front of the term. Okay. For example, if for this laminar flow, we definitely know the governing equation about the flow motion. It's just the Navier-Stokes equation, and given that equation, we can non-dimensionalize it or scale it. And figure out a dimensionless form of this NS equation, and we figure out two important dimensionless numbers, including Reynolds number and Flout numbers. So another type of thing is more interesting is that for some new physical phenomenon or newly discovered physical phenomenon, in that case, we don't know the governing equation, or we don't fully understand the whole process of all the phenomena. In that case, we don't have governing equation. We cannot do the scaling of the equation. So, for example, in additive manufacturing, we have a lot of complex physical phenomenon. For example, this chaotic keyhole dynamics. So for that problem, we don't have exact governing equations to describe the dynamics of the keyhole motion and fluid and free surface. So in that case, we don't have a set of governing equations or dimensionless numbers. So but we can do some experiments on that, and we can do a set of experiments with different input parameters, or even we can change the material system and see the response of the materials. And we can get a set of experiments, and based on that data, it's possible to get some dimensionless numbers from that based on traditional theorem, that is Birmingham-Pi theorem. We can kind of guess the dimensionless numbers for this type of problems, which we don't have governing equations. Okay, so the Birmingham-Pi theorem is the core of the classical or traditional dimensional analysis. So the procedure is like that. First, we figure out a causal relation between some input or independent physical quantities and one output physical quantity, and we want to figure out a relation between them, and we list the dimension of all the quantities, and they are our law of fundamental dimensions. In nature and science, we only have 7 fundamental dimensions, length, mass, time, electrical current, absolute temperature, amount of substance, luminous intensity. And for mechanical problem, typically we just focus on 4 of them. And dimension of any quantity is a power law. And this dimensional expression is equivalent to a dimensionless expression with fewer dimensional parameters. And after that, dimension of each parameters is 1 or it's dimensionless. And basically, the Buckingham pi theorem tells us try to answer how many dimensionless numbers are sufficient, not necessary to describe the same physical system. So assume we have involved n number of physical quantities which are expressible in terms of j independent fundamental dimensions or fundamental quantities. So finally, this system can be described in terms of k, which is equal to n minus j dimensionless parameters. So that's the maximum dimensionless numbers we need to describe the same system. But it's not necessarily the case. Sometimes we only need fewer dimensionless number because some of them can be ignored for some specific cases. But generally, the Buckingham pi theorem tells us how many dimensionless numbers are sufficient. And it involves the dimensional invariance. It's a general principle in nature and science that is all the physical laws should not change if we change the unit system. Okay, so if we use the length scale or time scale, we should not change if we change the unit system, we should not change the physical law. Okay. And in the literature, the dimensional analysis can be written in matrix form. So we start from a list of parameters or physical quantities, and we figure out the dimension of them, a dimension matrix of them. So each column is the dimension of the corresponding quantities. We figure out them and put that into a matrix. It's a known physics once we know the dimension. And we can solve the linear system W equal to 0. So the W basically is just the coefficient of that, the power of that scaling law, the power law of the dimensionless parameters in that case. And because it's an underdetermined system, we have an infinite many solution for this linear system, but we can figure out a set of bases, linearly independent bases for that system, and those coefficients are several dimensionless numbers for this system, and other dimensionless numbers are just the linear combination of those basis dimensionless numbers. And if the matrix, dimension matrix is full rank, so the number of bases is just equal to n minus j. So basically that aligns with the Buckingham pi theorem. Okay, so once we know the coefficient W, we can know the expression of the dimensionless number we want to compute or want to find. Okay, and eventually we can simplify the problem to a dimensionless expression. Okay, so but there are several limitations of the traditional dimensional analysis. The first is we solve this linear system and it's underdetermined. So we have an infinite many of solutions. So we cannot get a set of the dominant, or we cannot tell which dimensionless numbers is more important than the others, which is true for many physical systems, but mathematically we cannot tell. So we cannot figure out a unique and dominant set of dimensionless numbers that actually governs the physical system. And also another thing is that we can only find a few dimensionless numbers, but we don't know the relation between them. Okay, the relation between them can be nonlinear or linear, but we don't know the information because we just don't have a clue to find the relation between them using dimensional analysis alone. So that's why in recent years we're trying to overcome those limitations by introducing so-called data-driven dimensional analysis. So traditional dimensional analysis, we start from parameter list and figure out a matrix like that, and non-dimensionalize the equation and find n sets of dimensionless numbers. But relationship between them is still unknown. But for the data-driven one, we still start from the parameter list and dimension matrix. That's the information we know, and we also have data. Okay, so we can collect a set of data. Basically, for example, if we have a experiment or facility, we can change the parameter P1, P2 until change some of those P input parameters and measure the resultant or measure the output parameters. And so that we can repeat this process and we can collect a set of data points. And
Zhengtao, I have a question.
Yeah.
What kind of data do you have? Because you have data on the state variables, but let's say you don't have, let's say the example that you had of the free surface where you have the Reynolds number and the fruit number. If you don't have information about the free surface, you have lots of data, but if you don't have information about the free surface, you wouldn't know what the fruit number, it cannot be determined. So the type of data that you have is very important. So can you say something about that, given data on all state variables equally?
Yeah, that's a good question. Yes, we still need to determine this parameter list. So that means what kind of parameter we are interested in. That's very important for our dimensional analysis. We need to determine what's our dependent, and we also need to make sure we include all the important parameters to measure in this system. If we like miss some important parameter, then we cannot get the good result.
No, I'm not talking about the parameters. I'm talking about the data, given data. Data on what state variables? All state variables. If you have a system like a system of equations, like in the example I gave you, do you need data on all three components of velocity? Do you need data on the elevation of the free surface? Because that's impossible to have. And
for that case, for some data cannot be measured from the experiment. That's true. But for some experiments, we can measure many quantities, and for many problems, that's good enough for figure out the dimensionless numbers. Okay. For example, in Reynolds numbers case, we don't need the velocity at any location. We just need the average velocity at the cross section, over the cross section. That could be good. And also we can measure the pressure drop between the input and output. So we can measure some of the data like that. Sometimes it's good enough, sometimes it's not. So that depends on how do we design the problem we want to solve. Okay. I will show you some examples.
I mean, there is this issue. There's also the issue of conflict in the dynamic similarity, which goes through the non-dimensional numbers. For example, you cannot have a model where both the fruit number and the Reynolds number are the same. That's a classical example of breaking down of the dynamic similarity. So that's why it's important to kind of think what data realistically you can have for this type of scaling. Not simulated data for that will come from the experiment. That is what I'm talking about. When you say given data, I think you assume measurements, not simulated data.
It can be experiment data or simulation data, but I personally prefer experimental data. Yeah, because for simulation, we already know all the physics. That's why we can do the simulation. But from experimental data, we might discover some new physics or new things from the data.
Right. Please go on. Thank you.
Yeah, thank you. Thank you for the question. Yeah. I need to think about those things. Yeah, that's very important. Yeah. Okay. So, but here we assume we already have a set of data, and we trying to combine those data, and data imply some relationship between the quantities, right? That's the missing information in the traditional dimensional analysis. So we want to combine the information in the data with the principle of the dimensional analysis together, so that we can get better or we can get more things as the traditional dimensional analysis. Okay, so in that way, typically we can identify the dominant dimensionless numbers, and we can find fewer dimensionless numbers, and the rest of them are just can be ignored. They are insignificant for the problem. And we also can find the relationship between the dimensionless numbers, because we can identify the best fitting representation from the data. Okay? Because we have the data, we can find a relationship, but we want to find a relationship between dimensionless numbers rather than just between the parameters. Okay. So here we try to figure out a formula or method of the data-driven dimensional analysis. We also start from a set of parameters we want to explore. And we also have a set of data. We can change some parameter and measure the output parameter. And we have n pairs of that data. And we combine these two together. We want to figure out something. In this slide, I'll just assume we only care about one input dimensionless parameter. It can be more, but in this slide, I just show one. And we assume Q is already a dimensionless parameter, just to simplify the method. But in our paper, we have a more general theory about this formula. Okay, so eventually, we just want to figure out this expression. The Q is equal to a function of pi. Pi is our input parameter, which is a power law of all the input quantity P, and the unknown is just its powers, W. It's a vector. W vector is our unknown. Once we know the W, we can know the expression of our dimensionless number. Okay, and the way we combine it is we figure out a constraint optimization with the L1 regularization problem. So basically, we want to, because we have n sets of data, we want to minimize the mean square error between the data and the predictive, the expression of our dimensionless expression. And there are two sets of unknown. First is our W, that is the unknown for the dimensionless number. And we also, another set of unknown is the beta. Beta is used to parameterize the function, because its function is unknown. But we can use some function parameters to describe, approximate that function. We can use a polynomial function or neural network that include another set of unknown parameter just to describe or approximate the function. So we need to minimize these two to optimize these two sets of parameters. And we also add the L1 regularization because we want those W coefficient as small as possible. That's the case in typical dimensionless numbers. And it's a constraint because we want to make sure the D times W equal to 0. D is the dimension matrix. So if the D times W equal to 0, that means the W is the coefficient of dimensionless numbers. So in this condition, we want to make sure we figure out the pi is the dimensionless number. Okay, so once we figure out this expression, we can that's basically the method of data-driven dimensional analysis. So for this function, it's an unknown function, but we can assume some function to fit the data in that way. Typically, it's a nonlinear function, so we can assume it's a polynomial or neural network, or even a differential equation if we know some differential equation between the parameters. So for example, we can use SIMD method to try to identify the equation in that case. And some people have tried this. Some people try to use neural network to solve this expression, to solve this problem for data-driven dimensionless number. We submit paper last year using neural network to solve the problem, and also two papers also published recently. One is from Stephen Brunton and Nathan Cruz from UW, and another one is from researchers from Chinese Academy of Sciences. Basically, these two papers and my papers were submitted at almost the same time. Okay, so once we figure out this constraint optimization problem, there are multiple ways to solve it. We try to directly solve it directly, but for many problems, it doesn't work because sometimes it's very hard to like find a converged result. So in this paper, dimensionless learning paper, we trying to use a two-level optimization scheme to solve this optimization problem. It's kind of straightforward because we have two sets of unknown variables, right? Can we just separate them and solve each of them separately? So we figure out two substeps. So for the first step, we just fix the beta and just solve the W for the dimensionless numbers. So, and we need to constrain the DW equal to 0 for this step. And once we can get a W and we fix the W and update beta, so that's another substep. And we can iterate between these two steps again and again until we get a converged result, until we get a minimum loss function. So you can see there are multiple benefits of this kind of two-level optimization scheme. The first, we can use different methods for these two steps, and because these two sets of unknown W and B have quite different range and different physical meanings. The W basically have a physical meaning. That's the power of the power law of the dimensionless number, and they are typically very small and rational, and sometimes they just like it's integral. It's -1 or 1 or 2 or 0.5. So we want to try those a small and nice number first. And we prefer zero order optimization because it's a rational number. So we don't want to explore all the decimal values. Also, we prefer to use a grid search or pattern search for the first step. And the second step is the standard regression problem, because in the first step, we already consider this constraint. So the second step is just a standard problem. We can use any other method to solve it. We can use neural networks or just polynomial regression or even tree-based method to solve it. And so that's basically the two steps we figure out to solve the problem. And next, I want to show you some examples we try. For example, the first example is we explore the turbulence Rayleigh-Bernoulli convection. So we have it's a non-isothermal buoyancy-driven flow, and we have a two plane with a distance of edge, and we have a thermal gradient, a temperature gradient between these two planes, and we care about the heat flux Q goes through these two planes, and because there is a temperature difference, so we have a flow. Basically, that's a buoyancy-driven flow between these two planes. And so the heat flux depends on the geometry, depends on the temperature difference, as well as depends on the fluid properties like thermal conductivity, expansion, viscosity, and diffusivity, and so forth. And we can figure out a list of parameters, and our output depends on those parameters. And we can collect a set of data to change, for example, change the geometry and change the temperature difference and change the materials, so that change the material properties, and measure the different, just the heat flux between the plates. And in this case, we collect some experimental data from literature, 182 experimental data, and we know the dimension matrix, and we know the dimension of all the parameters. And in classical fluid dynamics and thermodynamics, we know for this problem, we have two important dimensionless number. The first is the Nusselt number, and another is a Rayleigh number. But in this work, we assume we don't know those dimensionless numbers, but we just know the data. We just know the dimension of the parameter, and we want to put the data and dimension matrix into our data-driven model, dimensionless learning, and to do this two-step optimization. And after that, we want to go through all the possible weights of the dimensionless numbers and figure out the mean square error or two R-square mean square error or this R-square value for that fitting. So we find that only at one location that corresponds to W, that is our optimum W, optimum expression of the dimensionless parameter. And in that location, we can fit the data best. And in that location, we realize the expression is just the Rayleigh number. So in that case, if in this example, we use research to search all the possible weights within the domain we like. And for the second step, we just use polynomial regression to do the fitting, because we assume this problem is simple enough. So, and we can rediscover the classic Rayleigh number from the parameter list, even though we don't know the expression of it before. And if we assume our output is the Nusselt number, so we will find the Rayleigh number is our unique, like it's our global minimum. That's only one dimensionless numbers. number in this problem. But if we assume our output is not Nussel number, it's just a heat flux, we might have a more, and we might discover more dimensionless numbers. For example, in this figure, we show that it's not a classical dimensionless number in the literature, but we discover it from this optimization problem. And we don't know the name of it, but we find this relation between these two dimensionless numbers is pretty good. It's a linear expression. It's even better than the Rayleigh number. So in using this way, it is possible to find some new dimensionless number if you have a very good data set or a carefully designed data set. Okay. And for another problem we want to explore
Zhengtao, I have a question for this problem.
Yeah.
Okay, so for this problem is well known that actually the Nussel number changes as a function of the Rayleigh number, and there's a what's called the knee. There's like almost a discontinuity. There's a discontinuity in the slope for sure. There's a continuous curve, but the discontinuity in the so that's well known from strong turbulence. So that, in other words, W is not one constant. Your W1 is not one constant. It could be like 3 different constants. Another example I can tell you, when you have even diffusion and you have anomalous transport, you go from super diffusion to subdiffusion to standard Gaussian standard diffusion. So in other words, you don't have T to the 1/2 all the time. You can have T to the 1/3, or it could be super diffusion will be T to the 1.1. So these W's are not constant. So what you are doing now, you're zooming in into locally into one region, not for all Rayleigh numbers. Because if you look at the literature for this problem, which is beaten to death, you will see that it's not just one number. It's not just an exponent of Rayleigh to the 0.8 or something. So the W's are, here you assume the W's are constant, right?
Yes, W is a constant.
That's what I'm trying to tell you, that as you go through mixing, for this, especially for multi-physics applications, that's not true. It's just not true. And you can look up the literature and you can see you can see this. There's a physicist in the University of Chicago who studied actually this problem a long time ago.
George, this is Martin.
Yeah.
I just add that the Prandtl number is another parameter, nu over kappa, and for air it's 0.7, for water it's about 10. So as you do different experiments, you find different ranges for the Nussel number there.
That's right. So there's a Prandtl 1/3, but I think he keeps here the constant. But you're right, Martin, because also the Prandtl number to the power, if he includes the Prandtl number, it will be to a power, but that power, which will be another W, changes as you go from laminar to turbulent to strong turbulence for this problem.
I think in this case we just consider one stage of the whole problem, because the data we collect from the literature, they mostly in the same range, or a small range, not cover all the physics in the data. So that's why we only just consider a set of the physics.
You can look at Leo Kadanoff. I think Leo Kadanoff was a physicist there at the University of Chicago who studied this, these anomalies and so on. But there are lots of data that show for this problem, not other problems, but for this problem. Also, I think Martin Srinivasan also wrote about this transition through turbulence, actually, and then there's another stage. So it's not, I mean, that's why I have to be careful that this analysis is local. Unless you make W a function of itself, which then defeats the purpose. But W is not a constant in the entire regime of these non-dimensional parameters. That's an erroneous assumption.
You mean the expression of the Rayleigh number change?
Yeah, the Rayleigh
That's
is
a
not,
constant, right?
no, the Rayleigh is fine, but you have Rayleigh to W, let's say 1, right? That W1 is not constant.
Mm-hmm.
It
Yeah,
may be
I mean
piecewise constant. Piecewise constant.
Yeah. Here the relationship between the Nussel number and Rayleigh's number is not a constant or linear. We assume a polynomial to fix the relation. So the W is just describe the Rayleigh's number, Rayleigh number. So once the Rayleigh's number is unchanged, our W is a constant. But how the Rayleigh number affect the Nussel number, it can be any function. It can be nonlinear function. And we assume a polynomial to describe this region. Yeah, we use a
so what is W
order.
here? For this problem, what is W? What
W is, basically W is just the power of those parameters.
Like what
W
power?
is, for example, just W is just describe the relationship between the parameter and dimensionless number. So, for example,
right.
W
so
here,
So so P1.
P1, for example, is density. P2 is the delta T, for example. So the W1 is just 1, or W2 is -1. So once we know the W, we know the formation or expression of Rayleigh number itself.
So W, are you assuming that W's are constant or not as a function of?
The W is a constant, yes.
Right, well, that's what I'm saying. That's exactly what I'm saying, that because for large delta T, for very large delta T for the convection, W is not constant. That's exactly what I'm saying. It's not constant for very strong delta T.
Yeah, that could be interesting if we consider.
The simple reason is that the Boussinesq approximation is not valid, for example.
Yeah, that could be interesting if we consider W is not a constant. Yeah, that can explore more problem or wider range of the physics, I think. But in this work, yes, I assume W is a constant. Yeah. So yeah,
thank you.
Yeah, thank you for the question. Yeah. So yeah. If we can collect more data and wider range of the physics, so we can modify the method, the current method, and assume maybe some non-constant weight parameters, and maybe different stage we can figure out different kinds of scaling laws. That could be interesting, yeah, in the future. That could be a future work. Okay, but currently we just try another set of problem that is the depression dynamics in laser material interaction. That's a more complex problem involving more parameters, involving 11 parameters in this case, and we can do experiments and by changing those parameters and figure out, we are trying to figure out the dominant dimensionless parameter for that problem. And we basically go through the same procedure and explore 90 experimental data with different parameters and materials, and use basically the same procedure of the dimensionless learning. And once we go through the whole procedure, we identify only two minimum or maximum, and one is like a local maximum of the R square. And in that local maximum case, we figure out a dimensionless parameter like this. But if we use this local maximum, the data is scaled a little bit. It's not like collect into the same we use a global minimum that is this expression of the dimensionless number. So the data is looks perfect and it collects into the same curve, and it's a linear expression between the output and input. And so in this problem, even we have 10, 11 quantities, so eventually we only need 2 dimensionless numbers to describe the problem, and this problem is kind of a linear problem. So that's the result cannot be obtained by traditional dimensional analysis. Okay, so that's the expression of dimensionless number we figured out. We also try some more other engineering problem, for example, porosity in 3D printing, and explore, try to identify the key dimensionless numbers that control the porosity in metal 3D printing, because that includes more parameters and more complex relation. So in the step 2, we use XGB boost method to describe the relation, and we identify 2 dimensionless numbers at the same time to describe this porosity data. So in engineering, people just use energy density to describe that, but it cannot explain all the experiments with different materials, and it is not dimensionless. But after our method, the dimensionless learning, we figure out 2 dimensionless number to scale this problem and can fit all the data pretty well within the same surface, and we can explain the physical meaning of the dimensionless parameters. And we also try another example using simulation data, and we combine this dimensionless learning with SINDI method to try to discover the governing equation, but it's like dimensionally homogeneous governing equation. Traditional SINDI is just figure out this governing equation, but the coefficient of the equation is just a number. There's no dimension to it, or it's not dimensionless. So once you change your parameter in your simulation, you will get different number for your equation. That means your equation is not universal or general, but if we combine dimensionless learning for that, we can identify a dimensionless governing equation, including such as Reynolds number directly into the equation. And in that case, no matter how we change the parameter into the simulation, we can always get the same equation for that. So this is a simple example to show how to combine our method with the SINDI to identify dimensionless governing equation. Okay, so basically that's a few examples I want to show today. And in our paper and supplementary materials, we have more examples, including some example in solid mechanics. So in summary, so we propose this dimensionless learning to identify physically interpretable features and equations from data, and it's a flexible method, and we try to formulate it as a 2-level optimization, and it works with the noisy and scarce experimental and simulation data, and we're trying to add like 1% of noise to the simulation data to test the method. And it's particularly useful for engineering problems involving many parameters with different units or dimensions. So we are trying to use this method to explore more engineering problems, including manufacturing and other problems. Okay, so basically that's the talk today. So this is our paper, and we also have online documents and code, and we share the code and data in GitHub. So that's the talk today. Thank you very much for your attention.
Thank you. Is there any question for our speaker?
Yeah,
George,
may I ask
yeah,
okay.
go ahead.
Sorry, may I ask a question? So I have a question also regarding the searching for W. Yeah, so sorry, I don't know that much about the physics. So you mentioned that you assume these W are kind of integer numbers. So yeah, I'm wondering, like, you have to do the grid search. You mentioned the slow convergence. Is that because of this restriction of the W?
No, we don't assume W is an integer number. So physically, it should be just a rational number.
I see.
But yeah, but
yeah.
sometimes it is integer.
I see. But yeah, so I'm wondering, you mentioned that if you just solve for this constraint optimization problem directly, right, optimizing for W and the P together, W and the beta together, that's kind of very slow convergence, or like you don't find the optimal solution. Why is that? Is that because of the non-convexity or identifiability of this optimization problem?
Actually, I'm not quite understand this one. Yeah, because I'm not a mathematician.
Oh, no, yeah, I'm just
yeah,
curious.
we just try to solve this problem, but it works for some simple problem, but for some complex problem involving more parameters, sometimes it just fails. So we haven't figured out a reason why it cannot be solved.
I see. So it's related
Honestly,
to the dimension of W, actually. So the larger dimension it's more likely to fail. Yeah, and it also depends on the relationship between the parameters. For some problem, that relation could be very complex, and for some problem, it's even linear. So that's very easy to solve.
Yeah. Zhengtao showed the convection example. There, it was like square root of kappa nu. So it was like nu to 1/2. So that was like not integer. Yeah. I see. Yes. Yeah, because I was thinking originally I thought it maybe because of this integer. So he has to do the integer programming, makes this searching so slow. Yeah, but if it's like such a continuous optimization problem, I was wondering maybe it's the optimization problem itself caused this such a slow convergence. So yeah, I'm also curious, when you do this iteration, this two-level optimization, do you have to do the sub-step only once, or how many iterations does that require between the sub-step 1 and the 2? We have to do many iterations. Yeah, depends on the problem. I see. Can you tell us how many? Like hundreds or 200. I see. Yeah. I see. Yeah. So I'm wondering that from your intuition, is this the value of W and the beta, are they unique? So for example, is that possible that if I say change the value of W and then change the value of beta simultaneously, then I'm going to get the same loss function, the same value of loss? Yeah, that's possible. I would say not possible. I see. Yeah, depends. It also depends on the data. For some data, we find that W is unique. For some problem, for some data, we find we might have several equivalent W that give us different dimensionless numbers. I see. So that might be the non-identifiability. I see. Yeah, I'm curious about that because so George, I don't know if you remember our no-curl algorithm. So this architecture actually looks like one of the algorithms that I have developed before for solving the causal discovery problem. So we have a similar issue. So basically we have, like, say, two variables. We need to optimize them together, but the solution is not unique. So we developed what we call, we also had to do a two-level optimization,
But what we do is we try to develop what we call the projection method to kind of cut the sub-iterations. So you don't have to solve that many sub-iterations. If you are interested in that, I can send you a copy of our paper, and then maybe we can discuss further.
You can put it on the archive. Sorry, on the chat.
Okay.
That would be great.
Zhengtao, we have a question from another George from Johns Hopkins, George Kevrekidis, GK.
Yeah, we have the same initials. Hi, so thank you for this. It has been really interesting. I have one question, which is related to the number of variables that you can sort of reduce every time you perform this optimization. So in general, in pure dimensional analysis through Buckingham Pi, the only number that you can reduce is the rank of the dimension matrix. Whereas you seem to reduce more variables, and that is dependent, or the reason that it's possible seems to be that you sort of specify the important output that you care about. Is that a correct statement?
Yeah, we can reduce more dimensionless numbers because first, because we fit the data. So that means maybe in these data sets, some of the dimensionless numbers are not that important. So by going through that, our procedure, we automatically ignore some dimensionless numbers already. And also we might figure out some combination of dimensionless numbers together to become a new dimensionless number. So in that case, we can also reduce the number.
Okay, but then that is effectively a dimension reduction result that is independent of the dimensionlessness. Right?
Yes.
Okay, thank you.
Thank you.
Hey, may I ask a follow-up on that? So just about, like, I see you're using XGBoost, so and regarding choosing the right dimensions to reduce, right? You can do some feature analysis, like feature importance analysis, right? And then decide which dimensions are like based on the data, what's their contribution, and then you can decide exactly which one to reduce, right?
Yeah, that might be a good way. Yeah.
So I don't know how it's done in XGBoost. I don't remember actually, but like random forest can achieve basically same results usually and give you for free a very easy to use feature importance analysis based on the trajectories of all the paths in the trees. So even if it's not helpful, it might be interesting to see like which dimensions are more important, right?
Yes, that's a good idea. I think that's a good idea. Yeah. We might consider that. Yeah. We haven't involved that part yet.
Cool, thanks.
Zhengtao, it was really interesting, the experimental case when you had the additive manufacturing with the keyhole number. That was really interesting that you could, because that's a tough problem, and you were able to nail it. I think that was a highlight. But also, it was interesting to see how you can improve the drawbacks of a method like Cindy. So I was wondering if you try to combine this method with symbolic regression. We have Zhogren and Zhengtao, who is not listening today, unfortunately, but they're trying to do. I think Elam is on the call, who is doing symbolic regression after she's trying to discover the equation. So have you tried to check into that to see if that's possible instead of Cindy symbolic regression, for example?
Yes, actually, I tried symbolic regression, and I wrote a paper in arXiv about that. But I'm not sure if I used the correct or the best method about symbolic regression. And I find that the symbolic regression is quite slow. especially for the problem including many parameters, it's very, very slow to find the optimum. So that's the thing I find. So that's why I changed my mind for like this type of problem, which is faster, I feel.
Yeah, great, because there are several papers now that show that pins, for example, work very well if you use non-dimensional numbers, non-dimensionalization, the non-dimensional characteristic numbers, and so on. That's what there's several papers on that, probably. But that was excellent talk. Thank you very much for taking the time today.
Yeah, thank you so much for the invitation.
Yeah, Zhengtao, we're moving to the next speaker, and in case you didn't notice, you had left you some messages in the chat, so you may want to check them out.
All right, thank you.
Yeah. Okay, guys. Our second speaker is Jiequn Han, who is a research fellow in the Center for Computational Mathematics, Flatiron Institute, Simons Foundation. His research draws inspiration from various disciplines of science and is devoted to solving high-dimensional problems arising from scientific computing. His current research interests mainly focus on machine learning-based multi-scale modeling and high-dimensional partial differential equations. Jiequn Han holds a PhD in applied math from Princeton University, a Bachelor of Science in Computational Mathematics, and a Bachelor of Arts in Economics from Peking University. So without further ado, welcome, Jiequn, and you may want to start the presentation. Yeah, I see your screen now. Yeah.
Okay, so thanks a lot for the introduction. So can you hear me properly?
Oh, what's that?
Can you hear me properly?
Yes.
Okay, so let me see if I can highlight my mouse so that you can see. Okay. Can you see my mouse moving?
Yes. Okay,
great. Hi everyone. So first I will thanks to Professor Karandakis' invitation. I started to focus my research on using machine learning tools to solve high-dimensional scientific computing problems in 2016 when I was a graduate student in Princeton. Since then, I have witnessed so much exciting progress in the emerging scientific machine learning field, and I think quite of them were pioneered by the group here. So today it is an honor for me to have the opportunity to present my research work here. As you can see in the title, my talk is related to operator learning, which is nowadays an active research topic, much related to the development of deep ONet. But maybe I should highlight that our goal here is to address some long-standing challenge in developing constitutive models in multi-scale modeling, so which is a bit different from the typical context of operator learning. So I will explain that throughout my talk, and hopefully I can convince you that the operator learning is not only a powerful tool for PD solving, but also for physical modeling at the level of PDs. So this is a serious work based on the collaboration with the graduate student Xu Huizhou and Professor Heng Xiao from Virginia Tech. And at the bottom, I list our latest work, which is the main material of today's talk. So here is the overview of my today's talk. So I will start from the introduction of the Reynolds average Navier-Stokes equation, as the main example in our work, and introduce what kind of reduced modeling or constitutive modeling we want to do, and then we will introduce the problem setup and the methodology in the machine learning context, and after that I will introduce like two numerical examples based on that. One is emulating the Reynolds stress models through some synthetic data. And the second one is predicting the Reynolds stress in the, from data in direct numerical simulations. So before I go into the details, here is a high-level slide for the multi-scale modeling. In practice, in current computational physics, we often work with different scales, from the microscopic scale at the bottom to the macro scale at the top. So it is a common situation that we have some reliable physical models that works very well in a small scale, but that model is too complicated and expensive to simulate at a larger scale for the phenomena of our interest. So multi-scale modeling is a very general philosophy to deal with these kind of problems. We rely on we model the behavior of large scale systems using some reliable small scale models instead of relying on some ad hoc large scale models. So there are a lot of names related to this idea, like constitutive modeling, surrogate modeling, model closure, reduced form modeling, so which all have similar meanings in this context, and I may change them interchangeably in my following slides. And the recent advancement of machine learning, especially deep learning, has been proved very useful in this multi-scale modeling paradigm. I think it's fair to say one of the most successful example happens in the microscopic regime for the molecular dynamics. So we can learn some deep learning based interatomic potential accurately from quantum chemistry calculated data to leave out the effects of electrons and then speed up molecular dynamic simulations by several orders. So this is unimaginable even 10 years ago. The high performance computing implementation based on the deep potential molecular dynamics developed by my collaborators and I won the 2020 Golden Bell Prize. So what I will talk about today is in the similar vein, but happens at the microscopic scale at the top. So at these levels, physical models are usually described by partial differential equations, and we want to develop some effective reduced order PDEs with machine learning tools. So the research in this topic is relatively preliminary compared to the success in machine learning based molecular dynamic simulations, but I think its potential is equally exciting. So today I will use the turbulence modeling to illustrate what kind of problems we want to solve. So here is the Navier-Stokes equations for the incompressible flow. There are 4 unknown variables, 3-dimensional velocity u and 1-dimensional pressure p. So here are 1 plus 3, 4 equations. So they can be used to describe different phenomena, include the turbulence. But in turbulence, there are structures at different scales, like small vortices, middle vortices, and large vortices. So imagine the study of turbulence around an aircraft. So we may be mainly interested in the large vortices that affect drags. So we want to drop those fine scale structures and have a model for large scale only, so that the simulation is much cheaper. So this is in fact a very fundamental idea in fluid dynamics. Since Reynolds studied the turbulence, he proposed the so-called Reynolds decomposition, decomposing the field through 2 terms. One is the long time average, capturing the larger scale structure. So here the bar over the notation denotes this long time averaging, and the one is the fluctuation denoted by U prime. So using this Reynolds decomposition and apply it to the velocity and the pressure field with some algebra, we can derive the following Reynolds average equations, Navier-Stokes equations called RANS. So it is a static equation since the time effect is averaged out, and it has a very similar structure to the original equations due to the property of decomposition. The only new term is the tau appearing on the right-hand side. It is a 3×3 tensor called the Reynolds stress tensor, defined as the time average of the second-order statistics of the velocity fluctuations. So at first glance, it makes the equation more complicated since right now we have 4 equations, but more than 4 variables, and we need some additional relationship using velocity, capital velocity U and capital pressure P to express this unknown Reynolds stress tensor, so that the reduced PD is still solvable. But the hope is that if we can find some reasonable relationship mapping from capital U and capital P to this tau, the reduced PD is much easier to solve because we can drop out those fine scale details and find that reduced range equations can provide us physical information at a large scale. So in today's most industrial applications, the range equations are still the workhorse tools, where high fidelity methods such as direct numerical simulations or large eddy simulations are too expensive. So in this sense, turbulence closure problems, it has been the central topic in turbulence study for a very long time. And from this example, you can see the goal of the closure problems or constitutive modeling is to find a map from the primary variables of our interest to the unresolved variables, so that the reduced order PDs are closed or solvable. So in the context of turbulence modeling, it is using mean flow velocity and mean flow pressures to express the Reynolds stress. And another typical usage of closure modeling happens in the kinetic equations called the moment closure. People there want to use moments to express reduce the moments to express unknown flux and the source terms. We know such kind of mappings, described here, will never be exact in general because we will lose some information in the unresolved variables. But we hope the reduced order PDs can provide us an approximating solution with much lower numerical cost in computation. So by the nature of this goal, you can see that such closure problems are very suitable for machine learning. We can simulate the original equation to collect the data and use supervised learning to obtain some good closure models through the regression. So the learned closure model or constitutive model will be after learning will be a part of the reduced order PDE, and we can use it to simulate physical phenomena of much larger scales with affordable computation costs, and we can even use some traditional numerical algorithms to solve those kind of problems. So in this sense, the machine learning based constitutive model is as transparent as those traditional closure models developed using human knowledge or ad hoc approximation. The hope is that we can use machine learning tools to find better closure models, especially when the input for the closure model is high dimensional, such that the traditional model methods do not work.
Jiequn, can I ask you a question?
Sure.
You assume
Sure.
that this approximate this mapping that you're trying to approximate is exists and in every flow, and it's I guess it cannot be unique, but you assume that there's always a mapping like that? Oh,
that's a very good question. So I should clarify a little bit. So I have already clarified a little bit. So we will not expect those kind of mapping exist universally for all the kind of data. So because you can think there are always extreme or adversarial examples, so that the mapping will lose its accuracy. And the hope is that we hope that we can find some approximate mapping or constitutive model that can work for a family of problems, so that if we know our problem of interest falls into that family, we can reliably use this kind of closure modeling. But you are right. We will not expect those kind of mapping exist or work universally well for all the kind of problems.
Can this be expressed in terms of like the Kolmogorov spectrum, for example, when we do LES, right? We know that we have to capture, let's say, 1/3 of the cascade, the implicit cascade, the self-similarity, in order to get reliable results. That's a rule of thumb. Here, when you do runs, if you are really, really coarse, right, in that growth energy spectrum, and you just touch the tip of the whole spectrum, it's gonna fail, right? So the assumption should be that there is, I mean, there should be some sort of a ratio of what you resolve over what you don't resolve. Let's say compared to Kolmogorov, dissipative scale, to tell you if that's possible or not, right? But you're not looking into that. You assume that you have it and you try to find a method to.
Yes. So you can, in some sense, you can think, okay, I'm trying to find, okay, given the coarse grain variable defined as the time average quantity, I should find some mapping as good as possible in my machine learning capacity, so that I can use that model to solve runs only to get some good approximation to the larger scale solutions or a long time average solutions in this runs context. Is that clear? Will answer your questions.
Yeah, well, I mean, it's a difficult question. I was just trying to see if you have thought about it, but yeah, that's fine. Thanks.
Yes, you are right. So all I have seen, or the hope, have to be defined on a finite and small set of applied data distributions. Otherwise, if data distribution can be arbitrary, it's impossible to achieve this goal. Okay. So yeah, so I think this, okay, the audience must be familiar that the intersection between PDs and the machine learning has received a lot of attention in recent years. And I would like to clarify that the topics I talk about here is different from two other very popular topics nowadays. Okay, first, it is different from using machine learning to find a solution to a single PDs, like what pins does or DBSD method for high dimensional PDs. Second, it is closely related to, but still different from using machine learning to approximate a solution operator to a family of PDs. Okay, so as far as I know, to the turbulence fields or Boltzmann equation arising in applications, direct machine learning based solvers are still incapable of giving reliable solutions due to the complicated physics. Okay, so this is the context of multi-scale modeling with constitutive models, and now I want to explain where another keyword in the title, the non-local operator, comes from. So recall that the goal is to use the mean flow and the pressure information, capital U and capital P, to predict the Reynolds stress, tau. Okay. Suppose we want to know tau or some quantity related to tau at a location X. So the simplest choice we can come up is to use the mean velocity U and the mean pressure P at the same point, as shown in this figure, and find some approximation, function approximators capital F to predict the target quantity. So this is called a local closure model, and it is widely used due to its simple form, as you can imagine. But there are many simple examples showing that such kind of a local closure model is quite limited. And the stress can be affected by the upstream flows or even downstream flows. So a more general form is to use information from a neighborhood of X, like the bottom figure, to predict the target quantity of our interest at the point X. So now the model form becomes a functional of the mean velocity field and the mean pressure field instead of a function taking only local values. So this is where the operator concept comes from. So it is certainly more expressive due to this operator viewpoint, but also much more difficult to construct and calibrate such kind of constitutive models. Okay, and given this non-local quantity, the next question is to consider is that, okay, why and how to choose a finite non-local region? Because if the non-local region is arbitrarily large, okay, you can imagine the computational cost must be very large. So so here I use a 1D example to illustrate our idea. So this is a 1D static convection diffusion reaction equation, for example. So there are some diffusion constant mu, velocity u, and dissipation cassette, and P is the production term on the other side. And in the linear case, we know the solution can be written with the Green's function, so where I use G to denote. So the final solution C at a point X is essentially a convolution between the Green's function and the production, okay? And if we plot the Green's functions, we know the Green's functions, okay, if we use relative coordinates X, since the problem is translation invariant, if we use relative coordinates to visualize this Green's function, we know it will decay very fast when the relative coordinates is far away from zero. Okay, so this is essentially indicated by the finite range interaction in physics. Okay, you will not imagine, okay, the point is very far away will have some immediate effect on the current point, and this kind of finite range interaction will justify us to truncate the neighborhood properly, so that we have a finite non-local region around the point of interest X. Okay, so we'll use the field in that truncated region as the input to our operator learning. And the specific size of this truncated neighborhood can be computed by the truncation error of the Green's functions. Okay, so that's the introduction of the non-local region. And the next thing to consider is that, okay, what kind of requirement do we have for the closures modeling, especially in fluid dynamics? Okay, and one important thing is the symmetry. Okay, this is a concept, okay, widely studied nowadays in a lot of contexts. So in fluid dynamics, suppose we want to implement a non-local closure model. Okay, so we need to, of course, in computation, introduce some spatial discretization. Okay, they are not necessarily fixed. So suppose in the non-local region, okay, here I use the ellipsoid to denote the non-local region computed from the truncation of the localized Green's function, and we will have some spatial discretization of this non-local region denoted by n points x1 to xn. Okay, and then we also have flow information, the mean flow velocity u1 and the un evaluated at these points. Okay, so for the notation simplicity, I am ignoring the pressure notation capital P. Okay, so the non-local mapping we want to find is essentially a mapping from x1 to xn and u1 and un to the Reynolds stress tau at the central point of our interest, denoted by this red cross. Okay, so what kind of symmetry do we mean when we talk about the constitutive modeling? Okay, first it should be translation. If we change the coordinate systems by some delta x, and then the u would denote the same. So all the physics remain the same, and we expect the stress should remain the same. And by a similar argument, if we rotate the coordinate systems by some rotation matrix tau, then this 3×3 matrix should rotate equivalently by this matrix tau. And of course, the inputs are also rotated by this matrix R. And the third symmetry is the permutation symmetry coming from this operator or a concept or the discretization of space points. Because it is an operator, it essentially is indifferent to the order of points x1 to xn, which means if we permute the index of the points sampled in this region, here I use sigma to denote this permutation, then the output should remain the same because they are describing essentially the same physics. And the last requirement is important in a lot of industry applications, because when we generate the mesh for irregular geometries, there's no natural index of the points. So guarantee the permutation image, the symmetry can help us get a more generalizable model. And yeah, so here I list at least three benefits to to preserve the symmetry in this kind of constitutional modeling. First, it respects the physics because essentially they are describing the same physics. And the second, because they respect physics, we expect to have better data efficiencies because one data, okay, if we guarantee, for example, frame invariance, so one data instance in particular will reflect all the physics laws on the different frame systems. And due to this kind of thing, we could also expect we can have better accuracy due to this kind of symmetry preserving. Okay, so we want to preserve symmetry, all these kind of symmetries in our constitutional models. So our main idea, okay, it comes from the something I have developed previously for modeling force field in molecular dynamics, because okay, due to the same physics, they have the same symmetries there. So to illustrate the main idea, so here I list a simplified setting. Suppose I have function f, okay, which maps a set of coordinates to a scalar output. So take x1 to xn as input. And our goal is to fetch this function from data and preserve all the symmetries simultaneously. Okay, so the first translation symmetry is relatively easy to impose because we can always compute the center and then use relative coordinates. So this relative coordinate system is invariant under different frame translation. And for rotation, we have an important property is that the inner product between different relative coordinate systems denoted by matrix D prime. Okay, if we write it in matrix notations, the D prime is invariant on the different on the different rotation of the frames. Okay, but the main issue of this inner product matrix D prime is that this matrix lacks permutation invariance because its ith column or ith row denotes the information respect to the ith point. So if I permute the coordinates index, then say permute in point I and point j, then the ith column and j's column and ith row and the j's row will be switched as well. So we needed to fix the additional permutation symmetry, and this symmetry space is a large one, especially when number of points n is large. Okay, so the idea is similar to the ideas in the literature called deep sets. So if we know function f is permutation symmetry with respect to its all input xi, then we can prove the function must be expressed in certain way in two steps. The first step is to mapping each individual component xi to some functions phi I. So you can think of phi I as embedding functions, and the dimension of phi I can be high in principle. And then we take the sum or the average operation over all the embedded factors and then feed it into another function rho. Okay, so here is a simple example showing the feasibility of this decomposition. Suppose we have one variable, we have two variable functions z1 and z2. So you can think this scalar output is permutation symmetry respect to z1 and z2. And then with some algebra, we can always rewrite the left-hand side with these forms so that we can design two embedding functions. First is linear mapping, and the second is a quadratic mapping. And then up with some algebra, we can show this row will serve the purpose with phi together. Okay, so the straightforward idea is that given this theorem, okay, we will parameterize these unknown functions phi and rho with neural networks so that the final function is automatically permutation invariant respect to the index of points. Okay, so that's the three techniques used to impose three symmetries, and we need to combine them together to guarantee all the symmetries simultaneously. So to that end, we introduce a set of m embedding functions phi k. And these embedding functions always take the magnitude of the relative coordinates as input. So the embedding functions is translation and rotational invariant. And then we do a weighted sum of all the coordinates. So in the matrix form, it will be written by G transpose times X, where G is the weight matrix provided by the embedding functions. And then in the matrix notation, we can finally get a symmetry preserving feature matrix by computing matrix L times L's transpose. So you can see this matrix, of course, it's permutationally invariant because this L, okay, by its nature is summation of all the points. So the matrix L is permutation invariant. So L transpose, the transpose is also permutation invariant. And since L itself is translation invariant, then the D is also translation invariant. And regarding the rotation invariance, we know X transpose is in the middle, is rotational invariant, and the weight G is also rotation invariant. So by design, this matrix is symmetry preserving. And then the natural idea is to make it a vector and feed it into another general function rho to get our desired output. Okay, so that's the main idea, to impose symmetry. And now let's get back to our non-local setting in the RANs. So here is a schematic plot of our network. So we call it vector cloud neural network with equivariance, because what the output we want to model is a 3x3 tensor. It imposes equivariance instead of variance. And suppose we want to predict a point, the stress at a point, we have a vector features attached to all the points around it. So it forms a vector cloud, and our model takes that vector cloud as input and predict the stress with all the symmetries. So to summarize, we use relative coordinates to ensure the translation invariance. We use inner product to ensure the rotation symmetry, and we use average embedding to ensure permutation invariance, and combine the three to get symmetry features. And we fit some invariant output. And okay, so this is denoted by the bottom right matrix E, and then we rotate it with the matrix X. So in this form, so that the final stress will be rotational equivariance. Okay, so far I have talked about the techniques about the symmetry preserving, but by construction, you may realize that the resulting model is also adaptive to different spatial discretizations, because in my embedding procedure, I compute the average of all the points. So if we have a different set of points, the whole network is still computable, because the embedding function is applied to each point, and the final fitting is applied to a fixed dimensions. So that means if our input changes, our training network can be applied without any modification. So that will increase the capacity of a network. We can train on different sets of data and apply to different discretization of data. Okay, so here is the flow features we used in our paper. So there are some vector features. The relative coordinates, of course, is important. The velocities is also important. And to facilitate the training, we also introduce some auxiliary scalar quantities like the cell volume. So because our data is generated by some finite volume solvers, and also the boundary, for example, the boundary conditions will inform us. So we inform the numerator operator to consider the boundary conditions when the point of interest is near the boundary. And yeah, it is worthwhile to note that for all the flow features, we will non-dimensionalize them by some quantities. So I think this is related to the previous talk by non-dimensionalizing all the features. So the random operator can have better generalizability to different flow fields.
Jiequn,
Okay.
can I ask you a question? Because
Sure.
the invariance, there was a paper long time ago by Julie Lin, I think, in general fluid mechanics, and
Yes.
she introduced the invariants, I1, I2,
Yes.
I3, or PQR, or whatever they call them,
Mhm.
which we also use a lot in Lumley introduced that long time ago in turbulence modeling in moments. So she actually got good results and so on. But are you saying that now that's not sufficient because you're looking at non-local? So
Yes.
these variants are for local as opposed to, so basically you extend that idea of the invariants to non-local with or non-local interactions with finite horizon. Is that what? At the high level?
Yes. High level, you give absolutely correct interpretation. I think the Julian Lin's paper is very influential, and that's a very nice formula to deal with local formulation if you want to fit a stress test output. But the main argument in here is that we want to incorporate non-local information. So that's why we have to go through this numerical stuff to devise an operator to emulating all the information nearby, so that it can be more powerful.
Yeah, great, thanks.
Yeah, that's a very good comment. Thanks. Okay, so now it's time to showcase our numerical results. So okay, this is the first setting. So in this setting, we are emulating a Reynolds stress transport equation from a synthetic data. So this is a PD model for turbulence modeling. So here we assume the velocity field U is given. So essentially it is a uncoupled PD. So it's different from the original RANS. We are only solving the sum concentration tau. The production term P is closed, but the added viscosity mu, the pressure strain rate phi, and dissipation tensor E are modeled by some existing turbulence models. They are all non-linearly depending on U, and we treat these existing turbulence models as ground truths so that we can have reliable solvers to provide us the data and to focus on the approximation errors of our neural operators. And the geometry we consider here is the periodical hills. So there are incoming flows from left and flow to the right. There are periodical boundary conditions horizontally, and we have hills on the left and the right hand side, and we have a parameter alpha characterizing the geometry of the periodical hills. So basically, the smaller the alpha is, the steeper the alpha, the steeper the hill is on the left on the corner, and so we will vary our geometry parameter alpha from 1 to 2 as our training data, and test the case from alpha to 0.5 to alpha equals 4 to so covering both in distribution testing and out of distribution testing. So to summarize, the learning goal is to take a group of points as input data, each having a feature vector attached to that, and the output is a stress tensor at the center of the cloud, so which is solved from the open form. And here is a visualization of the flow velocity field in different geometries. So alpha equals 1 is the steepest one in our training set. Alpha equals 2 is the most gentle slope in the training set, and we also have alpha equals 0.5 and alpha equals 4. So you can see if alpha gets smaller and smaller, okay, there's a larger and larger recirculation zone at the bottom, so which makes the flow complicated. And when alpha is large enough, okay, the flow is closer and closer to the laminar flows. And in our data generation, we set the Reynolds number about 10,000 as a regime. Okay, so we train, as I mentioned, we train our models from alpha equals to 1 to alpha equals 2, and we use the L2 loss functions between the Reynolds the stress as our loss functions, and here is some prediction result after the training is done. So here, because 3x3 stress tensor is hard to visualize. So here I plot the turbulence energy defined as a trace of 3x3 tensor for visualization. So in the in-distribution testing, we have alpha equals 1 and alpha equals 2. Okay, so the case is identical to the training, but it's still a valid test case, because you can imagine we will sample different points or different matches, okay, used in our testing compared to the points we used in the training. So the points used are different between training and testing, and you can see the predicted turbulence energy is quite good across a whole field for alpha equals 1, alpha equals 2. I think the first row is ground truth and the second row is prediction. Okay, they agree very well. And to see their difference more clearly, we plot out several cross-section profiles at the bottoms for both alpha equals 1 and alpha equals 2. You can see the black ground truth and red prediction agrees very well. And if we move out of the training distributions, look at the case of alpha equals 0.5 and alpha equals 4. Okay, so we do the same thing, and you can see, okay, qualitatively the whole profile of turbulence energy still agrees quite well, especially for alpha equals 4, but there are some noticeable, okay, deviations, especially for alpha equals 0.5. Okay, this is mainly because, as I explained earlier, there's large circulation zones at the bottoms, okay, which makes the flows complicated, and there are some unseen situations in training data, so that there are some difference at the bottoms. Okay, so here I plot the overall errors across different geometries from alpha equals 0.5 to 4. So the light regime is the training data regimes, and the dark blue regime is the out of distribution regime. So which is very common in other machine learning tasks. Okay, we have a very uniform small prediction error in our training regime, and as we go out of the regimes, the error increase, and this increase faster on the left side because the flows is more complicated. And I think this plot also partially answers Professor Kandak's questions earlier. So we will not expect, okay, we have a reduced modeling, okay, universal will for all geometries. Okay, so it's kind of more guaranteed for the data distribution we are covered, and we will expect it can extrapolate a little bit if the unseen data stays close to our training data distributions. And this statement is further verified in this plot. So in this plot, we plot the data distributions at various slope parameters, and so the left columns is for the interpolation regime when alpha equals 1.5, and the middle is the difficult side of expression when alpha equals 0.5, and the right column is the relatively easy side of exploration when alpha equals 4. So you can see in the interpolation, our features or data distributions, okay, noted by the red part, alpha equals 1.5, falls naturally between the boundary case when alpha equals 1 and alpha equals 2. Okay, and for the relatively easy set of exploration, okay, you can see the features still are encapsulated by the original data distribution when alpha equals 4. But the things was quite different when alpha equals 0.5. You can see there are some data distribution outside, there are some mass of data distribution outside of the original distribution. So this kind of area explains why we have worse errors for this difficult side of extrapolation. Okay, so that's our first testing case. In our second testing case, we move forward to even more realistic and more difficult situations. Okay, So because in real case, okay, we do not have a ground truth of turbulence modeling. Okay, what we can have at most is some real simulation data coming from direct numerical simulations. So here we apply our device, the vector cloud neural network, with equivalence to the data set of DNS. So this is a database with 29 DNS simulations coming out recently on the periodic hills. And okay, the geometry, the periodic hill stitching is similar to what I described in the previous situations. And again, we can train our model on the a set of training data and test it on a different case. So here I plot the component-wise the ground truth of Reynolds stress tensor and the predict Reynolds stress tensor. So you can see, okay, across the diagonal terms XX, YY, ZZ, and the off-diagonal terms RX, Y, okay, the profiles all agree quite well. And if we look at the errors, so here it is an interesting slide comparing the local model and the non-local model. So okay, again related to the previous questions. So here, although we are not using the tensor formulation of Julia Lin's formulation, so here we are using a neural network which guarantees invariance and use all the features, but they are restricted to the local point instead of the neighborhood region. And if we compare the performance of non-local model and the local model, okay, we find, okay, local model still give some random prediction, but the error is clearly larger than the non-local model. And these errors are more evident again in the lower bottom recirculation zone. So here the darker the color is, the larger the error is. So you can see for different components, the local prediction at the bottom is clearly larger than the non-local version in the middle row. Okay, and this is a slide showing another benefit of our proposed model about resolution adaptivity. So as I mentioned, our model is independent of the number of points sampled in the non-local region. So which means we can train on different scan cells. So here we show the error plots when we applied the trained model on different resolutions. So the non-local region is the non-local region is discretized by 50 points, 100 points, 200 points, to 400 points, or even 4 stem cell. Okay, so you can see as the number of points increase, our error decreases. But across different things, okay, they always give some rainbow errors as long as the number of points is large enough. And of course, you will imagine as the number of points increase larger and larger, the error will saturate to some point. Okay, so far I have explained the main results of our talk, and I have also highlighted the benefit of resolution invariance. And another benefit I advocated at the beginning is the importance of symmetry preserving. So here I'm borrowing the results from another paper to highlight the importance of firm invariance. So here we are also predicting some Reynolds stress related quantity, okay, from a non-local mapping. And the setting is there's an airfoil and there's a flow coming from, and we want to and we compute the resulting field. So this AOA denotes the angle of attack. So we compare our vector cloud neural network with another neural operator called the graph kernel network, Jiequn. And the original version of Jiequn does not have rotation invariance, and we do computation on 2 situations. The original Jiequn and the Jiequn with additional rotation invariance by our own designs. So you can see if the Jiequn model have rotational invariance, then it can give quite good predictions on different angle of attacks. And of course, not surprisingly, our VCN also have good predictions on the different angle of attacks. But okay, interesting thing is that if the original operator, the graph kernel operator, does not have rotation invariance, and we apply it to different coordinate systems, you can see if the training reference frame, the testing reference frame is identical to the training, okay, the top row, they have very good results. But if we rotate the training, the testing frame by 35 degrees, by 70 degrees, 90 degrees, or even 180 degrees, you can see the error, the performance deteriorates quickly. Okay, becomes non-reliable very fastly. So these results are highly sensitive to the angles of reference frame if you do not have the rotational symmetry. And by design, the VCN gives results independent of frames. So if we apply VCN, all the figures, at least for B, C, D, E, 5, F, they remain the same. Okay. Okay, I have 3 minutes. I will wrap up quickly. So the last thing I want to say is that so far I mainly showcase the results of supervised learning. But remember, our ultimate goal is not to supervised learning. Okay, our ultimate goal is some physical modeling. Okay, after learning the closure model, the non-local closure model, we want to use this as a part of rank equations, and we need to check whether the final solutions is accurate and reliable given our non-local closure modeling. So we have some preliminary tests on these more important problems for the scalar case of the in the context of a K-epsilon model. So you can see there are coupling between the learning and the PD solving of the final rank equations. And we find that again, for the situation where Reynolds number is about 10,000, if we take a K-epsilon model as the ground truth, our neural network prediction can give us results that is consistent with the original K-epsilon model across different cross sections. Okay, so this is evidence showing the applicability of our device non-local neural operator for the ultimate rank modeling and solving. Okay, so to wrap up, I think the main takeaway is that the machine learning based closure or the machine learning based continuous modeling holds great promise to develop reduced order PDs, especially for fluid dynamics, and ensuring physical symmetry greatly improves the training efficiency, accuracy, and generalizability. And for future work, we want to test the performance of the learned non-local closure model for other primary PDs, as I show in the first slide. And secondly, we also want to test and benchmark the VCNE on more complicated 3-dimensional flows. And the third, we want to include some tensor quantities of the mean flow information as input features as well. Okay, so I will stop here, and thank you very much for your attention.
Thank you. Is there any question for our speaker? George, do you want to add some comments?
Yes, there's lots of questions actually, but Jiequn, can you tell people where did you use your neural network on parameterizing the invariance part, the equivariance? Where you were using basically a solver, but somewhere, right? These results are not all from neural networks. If you can go through this, what you will call phi or D. Yeah, maybe you can go through this again, please. See where the neural network comes in.
Yeah, so I think for most results figures I show, I'm showing the results of supervised learning. So I take the velocity field as input, and our neural network compute different non-local region to compute the output at each point. And when neural network comes in, is that we use neural network to parameterize the embedding function phi here, This
Right,
phi
right,
is parameterized by neural networks,
Yeah.
and then the final output row is parameterized by neural networks. So this phi and the row are the only two neural networks we parameterize.
right. But you don't actually represent a non-local operator with neural networks.
It's kind of I would say the parameterization of phi and the row defines a non-local operators.
Right.
Because it's non.
Now it depends what you call operator. I mean, it's not here. For example, I would think that the whole. Okay, you mean the mapping from the resolved variables to subgrid variables that you call non-local operator. Yeah. Okay. But you didn't.
Yeah,
you didn't
that's what I mean by non-local operator.
You didn't tell us. So there's a. You didn't tell us about the how non-local is non-local. You're non-local. Is it like 3 points? 10. I mean, what is your non-locality? You didn't tell us the interaction radius or so. We use fractional fields to do this long time ago with a paper with Fang Yin. So there we have infinite horizon, but then we also use subgrid models with paper in JFM in a bachelor issue with Meneveau, and we did we truncated. So what was your truncation in terms of non-locality? Like
that's a
say,
good question.
You can point in the figure on the right, and you can tell us is it
Yeah. So the number of stencil points across the whole thing range from 80 to 100 1000. So this is the number of points used, but it's related to how dense our the mesh we are. So there are two concepts. One is that the region of the non-locality, the ellipsoid, choose, and then how many points are used in that region. So here, the number of points, is the second thing. And in terms of non-locality, the size of non-local region, it is related to the truncation of the Green's functions. So it's kind of order one in this situation, in our examples.
So what is it? I mean, in terms of a characteristic length, let's say the height of the inlet, how big is what's called the horizon in peridynamics, for example? What is your?
Yeah, so I think this picture will give. Yeah, I think this figure is the right one to answer your questions. So this is exactly the size of non-local region we choose. So you can see, so the inlet have height 2 or 3. So here I create the long axis of our ellipsoid have also 1, and the size will change because the localized linearized functions have different coefficients. That's why different points have different shape of the non-local region. But that's the relative size. I hope it can answer your questions.
Right, except you're using the concentration field, the linear, which is it's fine. I mean, there's even analytical expressions by the work by Kreiknan, as you may know, on this. But it is subjective, right? For example, I see at the inlet you use on the left you have a bigger size and then smaller size. So it's how do you choose? At every point you have a different interaction radius?
Yes, at each point, the reason at each point we have different radial size because at each point we have different linearized coefficient for the diffusion term, the velocity part, distribution part. So because that's kind of coefficients can be computed locally for different points, and they have different values. And then if we compute the Green functions, the cutoff can be different. That's why.
Right, but then it means that you have, unlike molecular dynamics, unlike peridynamics, unlike temper fractional derivatives, here where they have one cutoff radius, here you have as many cutoff radii as the number of points that you're using. That's a lot, right? Maybe Jiequn didn't like the question.
George, I think the internet was disconnected.
Right. Okay. Let's see if he can reconnect. But in our group, we were doing this. Fan Yin Song, when he was here, he published the first actually non-local modeling of RAN. So maybe he can come back and tell us.
So should we wait for a couple minutes for him to?
Maybe let him come in back. I think he will reconnect.
Okay.
I will not ask any more questions, so make this system unstable.
Oh yeah, he's back. Hi, Jiequn, you're muted.
Sorry, it just seems my network issue.
Yeah. So Jiequn, the question was, do you have the cutoff radius, which depends on each point? How every point has its own cutoff radius. That's a huge task.
Yeah, maybe I missed that point. So the way we compute radius is by computing the Green's functions for each localized linearized functions, and then we have an error tolerance called epsilons. So that means given each Green's functions, okay, we compute the truncated region so that the mass under the truncated region, okay, takes the 1 minus epsilon area of the whole Green's functions. So in that sense, as long as we choose epsilon tolerance to 5% or 1%, then we can compute the cutoff radius for each point.
Right. You can do that for concentration, but not for the viscosity. That's the problem. So when you go to the, there is a paper, two papers, one for concentration for nonlinear interactions. I forgot the name of the gentleman. I invited him here a few years ago to Japanese to present his results, because he has the linear case of concentration like you had with the Green's functions, and that's exact. And you can, but then he also had the viscosity, and that's not exact. That's an approximation. So it actually you can commit. You know, it depends on how you measure errors, but it's not an exact science, let's say.
Yeah, so that might be helpful to improve the data selections in our whole pipelines.
Yeah. The other thing I want to mention is Yu, who was here earlier. She actually has extended the GKN to a non-local version. I don't know if you know that paper by.
I'm still here. Hello.
Oh, Yu is here.
Yeah,
okay.
yeah. I can send that paper over the chat. Yeah.
So I don't know if you, Jiequn, if you use a standard Caltech GKN and then you put rotation to it. Is that what you did?
Yes, this is what I have done. Yes.
To parameterize the Green's function.
To parameterize the whole thing.
The whole thing.
Given the same non-local input, yes, we use standard GKN and GKN augmented by rotational invariant features. This is what I compare.
So in that case, with the airfoil, I mean, it was not that detailed. Basically, you show that because I don't know if you're looking at turbulent flow, probably you're looking at laminar flow. So in that case, only the symmetry was important. The non-locality was not so important. That's what you told us.
For that airfoil, I haven't checked the comparison between local model and the non-local model, but I guess the difference might be smaller than what I show here for turbulent setting. Because
what was the Reynolds number for the airfoil? What was the Reynolds number?
I think it's much smaller than this one. I forgot the number, but I think around 100 or a few 100,000 stuff.
100 will be very, very laminar. so the non-locality, that has nothing to do. Laminar flows are local.
I haven't tested whether it is how big is the effect of non-local in this case.
If you have Reynolds number 100, you don't need a subgrid model. If you don't have turbulent flow, you don't need For
yeah,
this flow to become
then
turbulent, you need-
maybe then I need to check the number of these things. Maybe still as large as that. But I think the flows in this situation, as you can see, is simpler than the turbulence setting. That's why I think the difference between non-local and the local model will be smaller than the turbulence.
No, not only that, you don't need a subgrid model. If the flow is not turbulent, why would you need a subgrid model?
But for this, I'm not talking about the. So what do you mean by subgrid model in this situation?
Are you using the RANS version here, or the you use RANS when you did the open RANS or not RANS?
No, I'm not using RANS, or I'm use a ground truth existing turbulence model. So I'm not talking about the RANS modeling in this situation. I'm mainly talk about the importance of symmetry in this context. So I'm not doing I'm not doing PD modeling. I'm doing comparison of supervised learning. Yeah, that's something I should clarify.
Okay.
Yeah, you are right. This is not about the RANS modeling.
I don't know if you know the history of non-local modeling, but it goes back to Prandtl, actually. Prandtl first introduced, it's in our paper, we have a history, but in a nutshell, Prandtl introduced a mixing length like the 1917 or something like that. And then later, 1930s, he came back with a shear model, which is actually non-local. Kolmogorov also, after his initial model in the 60s or late, even 70s, he also realized that he had to use a non-local model because his theory was incomplete. He wouldn't get, for example, intermittency. Intermittency would not be covered by the Kolmogorov. So when we first did the fractional models, we use a fractional derivative to basically have a universal law for the wall of the usage. So then in a paper, the more rigorous work was a paper with Patricio Di Leone is the first author in the General Fluid Mechanics special issue for Bachelor a year ago, where we analyzed what is called the Karman-Hawthorne equation for subgrid scales. That's an exact equation. So it turns out that, and this is all 3D DNS and wall-bounded flows, but also periodic flows in homogeneous flows. And it turns out that that actually the non-locality would show up there, and classical subgrid models like Smagorinsky and so on are over-dissipative as opposed to the non-local models. So you may want to look at that because that's a kind of 3D realistic flows.
Yes, this is really what I want to look into, to find some cases showcasing the importance of non-locality.
Well, yes, the RANS decomposition is kind of dated because right now people write the a triple decomposition, which was proposed by not the Osborne Reynolds, but Bill Reynolds. Bill Reynolds was a professor at Stanford, and Hussein. Hussein and Reynolds, there's a paper where they have the triple decomposition. So there's sort of the average plus the large scale plus the fluctuations instead of the old decomposition, which is not accurate. Based on that, then there's something called the Karman-Hawthorne equation for subgrid stresses, and that's an exact equation. So then you use that equation to evaluate subgrid stress contributions and the locality or non-locality. So in the JFM paper I mentioned, that's what we actually use. We use the Karman-Hawthorne equation for that. So you may find that useful as you go forward into the 3D. And
okay, yeah, thank you very much for the suggestion. I will look into that.
But I think your contribution is unique because you introduce invariances, equivariance for non-local operators, which is very, very important, I think.
Yes, as you mentioned, because Julia Lin already considered this kind of symmetries in the local settings, but we realize that when it is in the non-local setting, the questions is much more open. So we try to find some.
It's beyond fluids. For example, in fracture mechanics, you have non-locality, and so you need to impose, if we are to have a In my group, we're trying to have this operator, but that operator, we didn't endow the operator with this equivariance in rotation. So that's very important to have it actually there.
Yeah,
so,
I think this kind of requirement is universal for different constitutive models
That's right.
in fluids or mechanics, other mechanics.
But I said even fluid mechanics or in solid mechanics, if you write it in terms of the invariance, I1, I2, I3, for example, some data knows what I'm talking about, then you actually have that invariance. But if it's non-local, the operator is non-local, then you don't have it. So that's why I think your approach is universal both to not just to fluid mechanics.
Yes, yeah. Thank you very much for the comment.
Here is some data. Do you want to say anything?
No. I really enjoyed your talk. Wonderful talk. Josh, my laptop got switched off, so I'm from Kasha's laptop.
Oh, okay. Sorry about that. I stole it.
A wonderful talk.
Thank you. Yeah, and yes, thank you for sending out the reference. I'm taking a screenshot of that, and we'll look into that.
Jiequn, are you competing for Gordon Bell again this year, or?
No.
Okay. Congratulations.
Yeah, it just takes more time to test, to implement it in the high HPC setting. So yeah,
you're right.
We need more preparation before that to solidify the methodology and the whole pipeline, I think, before we move into that.
Zolgan, I think we're good.
Okay, so if there's no other question, thank you, Jiequn, for your wonderful presentation. And this is our this week's current seminar. Everyone have a good afternoon and a good weekend. See you next week. Bye.
Thank you very much. Thank you very much for attending. Bye.
Bye.